Share my screen. Okay, so let's see. So where we stand. This is the, you can see my screen, right?
Yes, sir.
Okay, so we are in week 6. Okay, we are starting week 6. September 20th is when instruction started. So as per our, and this is what we are at, okay? Starting to discuss the core of SAT solvers, okay, which also forms at a high level the core of an SMT solver as well. So we kind of already 2 weeks behind. Okay, so maybe we have some slack and we can make it up. So in any case, today we are. Yeah, so the subject of today is DPLL, okay, which is the algorithm that makes the core of SAT solver, and that's the thing. That's what we're discussing, and then I will be talking an extension of DPLL that works with various theories, and that is the super structure that is used in SMT solver. And then specifically, I will be talking about a specific decision procedures for a real arithmetic, a simplex algorithm, which would then lead to more specialized versions of simplex that people have constructed, designed, and architected for verifying neural networks. We call it ReLU-plex. In order to make up some lost ground, in terms of the time factor, I know we had missed one class, and I don't think we had a makeup class. But in any case, I'm thinking of having possibly a makeup class this Friday, if it is okay with you guys. Okay, so let's see how it goes, and we'll see. So that's the subject matter. So anyway, the assignment is due on November 3rd. So I hope you have got started on it. And since I have not heard from you, I'm assuming that you have any issues, questions, or problems.
Sir, there was just a small typo. I think in question 2B, there is no loop condition. Can you just scroll down a bit? I think while I2 x comma y comma z is just, there is a invariant and then there is true.
Okay. Yeah, correct. Yeah, so if there is, okay, I will correct that. Yeah, so you're right. So, but then, so let's see. So for 2B, do I also say this is general question for 2B. See, the loop invariant, still makes sense even when the loop is non-terminating. Okay, but I guess construct what I've said. Okay, so I think I can. Okay, so you could just assume, so this one has it, okay? So you could just assume it's the...
Yeah, I think it was x is less than 10 in the previous version of the assignment.
So you can assume same, you can use the same loop condition here.
Yeah.
But I think, when I started out, see, loop invariant, they can be loop invariants. Okay, the concept of loop invariant applies to any loop, even including the non-terminating loops. It's only the part that if you exit that this something holds good makes relevant only if the loop is terminating. Okay. So in that sense, yeah. So for now, for this particular example, I'll use the same loop condition. Okay, good point. Yes. Okay. So just use this. Okay. Good. So let me share this. It's already shared. So go full screen. Yeah, this is a picture that you've already seen. So what we are at is the DP, this part here. Okay. So SMT solver has a solver, okay, which works for the conjunctive fragment of various theories. What that means is that these solvers are assumed to check satisfiability of conjunction of atomic formulas that are drawn from that particular theory. Okay, so this can be linear theory of reals, linear theory of arithmetic, or it can be equality with function symbols and various other things, but it's the conjunctive fragment. The DPLLT, is the framework that is used to, and then there are things that can combine. Okay, at the other level, all these theory solvers going to what's called the core solver, which really combines, it makes a decision procedure for a combination of theories, but still conjunctive. Okay, that is conjunction of various formulas. DPLL is the part of the SMT solver that solves for arbitrary propositional combinations over these atomic formulas. Like, for example, you can have implications, disjunctions, and conjunctions of any Boolean connective. That is the layer, the DPLLT, that I'll start talking today. Today, I'll just be doing the DPLL part, that is just for the propositional logic. Okay, so decision procedure for propositional logic. And then in the next class, I will discuss extensions to T, in the presence of theory. And in the following class, I will discuss simplex, the decision procedure for linear arithmetic, real arithmetic. And after that, Madhukar will do reluplex, which is a specialized version of, which is an extension simplex to, in the presence of ReLU. Okay, so that's, you can consider as a special decision procedure for linear arithmetic plus ReLU. Okay. Okay, so the SAT decision problem. So what I'll be talking about DPLL. That is the name of the core algorithm that even today modern SAT solvers use, and that solves the decision problem for propositional logic. So what is this decision problem? Given an arbitrary quantifier-free propositional formula, check any of the following: satisfiability, either satisfiability, unsatisfiability, or validity. Okay, any arbitrary Boolean formula denoting a Boolean function. So you can use any Boolean function. For example, here I used exclusive OR, and any Boolean connectives. Okay, and this problem, yeah. So it's a problem to solve any one of these satisfiability problems. When we say decision problem, it could mean either satisfiability, validity, or unsatisfiability. Check for arbitrary formulas denoting arbitrary Boolean function. So this problem is NP complete. And so let me skip these slides. Okay. So before I introduce the thing, so there are some, I want to draw your attention to some easy cases. Okay, and I don't know if we went through this earlier. Did I or not? Okay. Did I show you some very easy cases for the decision problem?
No, sir, I don't
No,
think
I
so.
don't
Okay.
think so.
Yeah. Somebody else said something?
No, I just said no, I don't think so.
Okay. So in that case, let me quickly go through. See, I mean, we discussed normal forms, okay, but in any case, you are. I think we did discuss that. So I'm assuming that you are all familiar with the two very popular normal forms for Boolean formulas. One is the disjunctive normal form, where you express any Boolean function over a set of variables as a disjunction of what are called cubes. Okay, there is sum of cubes, where a cube is a conjunction of literals. Okay, where a literal is either a variable or a negation of the variable. Now, the satisfiability problem of when it is expressed in this normal form as a DNF, the satisfaction problem is very easy. Okay, because a cube, okay, which is a conjunction of literals, it's a disjunction of that, of several cubes. So in order for that to be satisfiable, at least one cube must be satisfiable. And a cube, which is, as I said, a conjunction of literals, that is satisfiable if and only if the variable appears with unique polarity. Because if you have a conjunction of both the positive and the negative version, it is not satisfiable at all. So, for example, if you have it in DNF, then satisfiability check, all you need to do is to make one pass through your formula, inspecting every cube in the formula, and then check if that is satisfiable. And checking a cube to be satisfiable just involves checking that there is no contradiction in there. So, otherwise it is unsat. So, for example, this is unsat because this has a cube which is not satisfiable. There is a contradiction there. Therefore, so if you're only if you get into DNF form, the satisfiability is quite efficient. Okay, it's not. Similarly, if you're only interested in validity, then if you can get it into a CNF form, then that can be checked in linear time. So, what is a CNF? Which is a conjunction of, it's a product of clauses, where a clause is a disjunction of literals. Okay? And this validity checking of such a CNF formula is also quite efficient, because every, in order for it to be valid, since it's a conjunction of clauses, every clause has to be valid. A clause is valid, which is a disjunction of literals, if and only if it has one variable that occurs in both polarity. Because remember that the validity, clause is valid if it is valid for all possible valuations of that. Okay, so which means that you can do that by just inspecting it, all the clauses in the formula once, to see if all of them is valid, which is true only if it has this tautology, okay, a literal both in its positive and negative form. So then you can say, why is it so hard then, the general problem of decision problem? Anyone?
Because when you convert it from other forms, this from like
Yes,
becomes
correct.
a potential term.
Yeah, so that's why I very carefully define the problem of checking either satisfiability or validity or satisfiability for an arbitrary formula, which can be expressed in any form. Yes, that is what. So going from DNF to CNF and vice versa can have a blow up in size of the formula. As a matter of fact, it can have an exponential blow up in the size of the formula. The size of the formula is usually measured in terms of the number of variables and the clauses if it is in CNF form. So that, when you go from DNF to CNF, the number of clauses can have an exponential blow up because you need to apply these distributivity laws and De Morgan laws, and that causes exponential. Now, SAT solvers, the DPLL algorithm that we will be looking at, we'll be studying today, they all assume that your input formula comes in as a CNF formula. So the core engine always assumes that it is in CNF formula. Therefore, obviously, you will get this obvious question if it is CNF, and if you start out with an arbitrary formula not in CNF, won't there be an exponential blow up in size in the conversion process itself? Okay. Yes, it is true, but this can be minimized, this blow up, by using a certain kind of clever encoding called Citon encoding, which introduces new auxiliary variables given a formula which is not in CNF. This is a way to encode it without actually, kind of converting it into CNF through introduction of a new set of auxiliary variables. Without incurring the exponential blow. So it introduces a linear number of, a new set of variables, linear in the size of the formula, linear in the number of connectives that are there, okay, Boolean connectives in the formula, only, without causing an exponential blow up in the number of clauses. Okay, so that encoding is, I have described it in these few slides. In the interest of time, I'm going to skip over those slides. I mean, you can go through those slides. By the way, this lecture, DPLL as well as DPLLT, as well as the simplex, the next 3 lectures, I'll be following the material as discussed in the Decision Procedures book by Daniel Cronin and company, okay, which I think I have uploaded the link to the thing. And this particular, DPLL is the subject matter of chapter 2, 2.2 through 2.4. Now, that also discusses this Citon encoding. And present-day SAT solvers, they do accept formulas in arbitrary, with arbitrary connectives, okay, a lot of them, but they do go through a pre-processing step, which essentially uses with Citon encoding to come up with not an equivalent, but an equisatisfiable formula, because it introduces new variables, and that so you can study these slides, okay, and get familiarized yourself. Okay, so I'm going to skip that and get to here. Okay, so this slide you have already seen, right? So you already have, we discussed this resolution inference rule and this Davis-Putnam, the DP in the DPLL stands for Davis and Putnam, okay? The 2 authors of the, among the 4 authors who are credited with coming up with the DPLL algorithm. So here you could use, repeatedly use resolution, okay, until you either get a contradiction or there are no new clauses, until resolution is no longer applicable, and then come up with that thing. So that is this is one of the earliest Boolean decision procedure for propositional satisfiability on a CNF formulas. So you could use that. So, but what is the advantage? Okay, this is just, we've already seen this. Okay, so this is just a resolution graph showing either a in this case contradiction. But if so if you've exhaustively applied all possible ways of using the resolution, then you can conclude that it is satisfiable. We'll skip through these slides. Okay, so what is the drawback of a Davis and Putnam strategy? Okay, DPLL is a kind of not an extension, but an improvement over the DP Davis-Putnam strategy. Okay, so this one is memory intensive. Okay, because firstly you need to keep not only the original set of clauses, but all the new clauses that are introduced as a result of applying your resolution inference rule. Okay, because resolution, you need to consider resolution between the new clauses generated as well as one or more of the original clauses as well. Okay. Now this, although this can be used to check satisfiability also, it is not very clear how you extract the models. If your original set of formulas is unsatisfiable, then a proof of derivation of contradiction bottom, tells you why it is, it's good enough. But in the case where it is satisfiable, you need to, it's important to show a witness, that is the extract. And there it is not clear what. I mean, you could extract it from a resolution graph, okay, resolution proof. There is a way to do it, but that is, kind of hard. Okay? But even more importantly, your size of the proof, that is the resolution graph, is very sensitive to the order in which you choose your variables in the resolution. Okay, if you make some very clever, judicious choices, you can end up getting a result, either contradiction or satisfiability result very quickly. If indeed you choose a different ordering of the variables, then it can be a very long proof. Okay, then people started coming up with various strategies. These are search strategies. Okay, in order to come up with small proofs. And DPLL procedure is one such. You could view it as one such strategy. Okay, which really biases the resolution towards doing resolution towards unit clauses and short clauses. Okay, that is the basic idea of the DPLL, which is an improvement of Davis-Putnam. So that's what I will be discussing next. Any questions so far?
Sir, like this Putnam is same person from Putnam exam.
Oh, I don't know. Putnam lab? I don't know what Putnam.
I mean, like there is a Putnam exam, something like that. Math exam, Putnam. So like,
I'm not familiar with that. Okay. So Davis-Putnam, I'm talking about DPLL. DPLL itself, the LL stands for Loveland and Long. Okay. So DPLL, see, resolution principle was invented around 1960. The DPLL algorithm came out in 1962 or 65, if I remember correctly. So Davis and Putnam have been there, that long. Of course, they could still be alive. Okay, so I'm, I was born before 1965. So I really don't know. Okay, so without having any information, is that Putnam logician? Computer scientist logician?
Like I just know that there is some Putnam exam. I thought this was related to that person. So
yeah, I don't know. I don't. Check it out. So that would
yeah,
be
I'll check it out.
historical anecdote.
Yeah.
It would also be interesting to check. I don't think Robinson, who invented resolution principle, is alive. Okay. Now, I don't know the DPLL people in the DPLL algorithm. That will also be interesting to see. I mean, yeah. So DPLL strategy, it really restricts to resolution, to unit resolution. A unit resolution is one in which one of the two clauses, binary resolution, take two clauses and resolves it over a particular variable, correct? So here, unit resolution, is called unit if one of the clauses is unit, okay? And then, more importantly, it uses backtracking, okay, in order to make the search more goal-directed, okay? So what is unit resolution? So it uses, as part of it, a workhorse called BCP. It stands for Boolean Constraint Propagation, okay? So it's really, I mean, I'm going to state what BCP does. This is the workhorse, okay, of this DPLL algorithm. By the way, even to this day, the core of any even modern day SAT solver is essentially DPLL. DPLL plus a lot of certain learning mechanisms and a lot of heuristics, very clever heuristics. And that's what make SAT solver so efficient in practice on a lot of practical examples. But it still uses DPLL even to this day. That's why it's important to understand DPLL and also its connection to resolution. Because if you were to the ends, it's because its correctness is very much based on resolution. Okay, so you may view it differently, but what is going on there is resolution, but a special kind of resolution called unit resolution. And BCP is all it does is applies unit resolution until you no longer can apply resolution. That's what I mean when I say apply unit resolution till fixed point. What are the rules of unit resolution? Okay, so here are basically two rules, but the third one, which is the contradiction which was there before in Robinson's resolution principle, is just a special version of this. So here it is. So you have a clause which is one clause which is unit, and another clause which need not be a unit, okay, which means that it has more than one literal, which has one literal occurring in opposite polarity. So this is just an instantiation of a special version of the Robinson's resolution. So you resolve that to make it into a bar. Of course, if P, it occurs same polarity, then you can just almost like plug that thing in there. Okay. So unit resolution is pretty much plugging this the truth value implied by the unit clause into the other clause. That's all that's happening. Okay. The interesting thing is that you can always get a proof just using unit resolution. So in the case where both the clauses are unit, of course, you can end up getting a contradiction. Okay. And that's so these are the So application of BCP just applies these three versions of these unit resolution repeatedly, okay, on the clauses of your original formula. So the application of when it reduces the application of unit resolution reduces clause to true, then we say that that clause, the non-unit clause in that thing, is satisfied, okay, because it reduces to true. So when it results in this contradiction, we say that it results in a conflict. So this one, the first rule can, of course, it reduces the number of literals in the non-unit clause. So it can result in, as a result of this application, this clause can become unit, okay, because it eliminates one literal from that clause. And that's why when it then becomes unit, then you can reapply this unit resolution, okay? And BCP consists of repeatedly applying that set of rules. So at the end of using BCP, when it reaches fixed point, you could either have reduced all the clauses to true, which in which case it is satisfiable. So that's why. So if as a result of the BCP it reduces to true, then it can, you say it is true, okay? Or if it is results in bottom, then of course it is false, okay? Of course, there is a third possibility. Neither, yeah. So there could be. This is the case when the entire formula reduces to, in which case it's not only satisfied, it's actually valid as well. So in the other case, it is unsatisfied. But the third possibility is there will be some clauses, some may be reduced to true. Even if one clause, by the way, one clause reduced to false, then of course it will be unsat, because the formula is a conjunction of all the clauses, and every clause has to be true. The other possibility is some of them will be, there'll be some subset of clauses which remain unresolved. What that means is that they are not unit. They're neither satisfied nor conflict, or not unit. What do you do in that case? Okay. So what DPLL does is it asks you to make a choice. This is a forced decision. Okay, it forces a decision on a particular variable, either making it, forcing it to either true or false. Okay, and then you repeat this. You recursively call DPLL by adding that forced. The forced decision leads to a literal. Okay. So what you did here in the first step was, if there were any unit literals in the formula itself, that is what you propagated. Okay, first. Okay. This, you are doing this forced choice comes after that. Okay. So then you add that as a unit clause to your original. Oh, this should be F, by the way, not, no, G. G is being assigned to your formula. That's fine. So you add that, and then you recursively call them on once on the result of adding the positive literal, that is, as well as the negative, and that's how that you do. So where is the backtracking here? Because it's a recursive procedure. So if this thing becomes, so you will have to, at any point, if you are, making a wrong choice, then you will have to, do a backtracking. Okay, here the backtracking is not explicitly visible because I'm using the recursive style of doing it. But so effectively, if you had a more loop style, non-recursive style, so that's where you will have to come up with a particular choice of variables may lead to a conflict in this part, in which case we'll have to come back up and then do the not P, consider the not P version, version of that. Okay, so that's where the thing is. So I will go through an example, so where the backtracking will be clear. So the important thing is to, so I hope you understand BCP. So let me go through the example and then hold your questions, and then I will go through the example and then you can ask your questions, unless you have very basic questions here. Any of you?
Sir, could you explain what does unit mean?
A unit is a special kind of clause. Okay. Okay. When described, what I mean by unit clause is a clause which has only one literal.
Okay, so like just P.
Either P or not P. Okay. So there is a dual version of this. I'm showing the not P version of it. You can also have P here, and not P can be in the non-unit clause in the unit resolution.
Okay.
Okay. So whereas DP used a resolution on arbitrary clauses, whereas here what I'm doing is I'm forcing the use of only unit resolution. But how do I create unit clauses if indeed if there are some unit clauses in the original formula, you propagate all of them first, and then maybe that propagation itself can result in either satisfaction or conflict. Then you're done. But if you end up having some unresolved clauses, then you will have to make a choice, and that's what this thing does. Okay, it's like making a forced choice on these variables, and once you make the choice on a particular variable, that is like if you make it a positive choice, you assign it 1, then it's like adding a positive literal. If you make that preposition variable take false, then it is like adding a not P. Okay, and after that you apply BCP, okay, through unit resolution. Okay. And if you, so does that answer? So, but I'm when you apply BCP, the clauses get transformed, okay, into one of these possible. This is the state of the clause can change from either unresolved, to become satisfied, that is if it becomes true, or false, then it will say it is there's a conflict in the clause, or it can become unit, or it can remain unresolved. Okay, so and then so it's only when you at fixed point, if it is unresolved, then you will have to make a decision. Okay, so here's an illustration. Okay, so a set of clauses. So
these are all and together, right?
Yeah, these are and together. Yes, that is true. So it is, yes, I show it as a set of clauses, but the formula is an and together. Okay, it's considered as a conjunction of these. Okay, so that's why, since it's a conjunction, sometimes the formula is viewed as a set of clauses implicitly assumed to be conjoined together. Now here is the starting point itself. You can't apply BCP. Why, Harsh?
Like, because I don't see any x1 and x1 not, x and x not.
Or rather, there's no unit clauses. Unit resolution can be applied only if there is at least one of the clauses unit, right?
Yes.
Yeah. So if it's unit, see, if a clause is unit, that is, if it has a literal, then there is then that, then a decision is made, because every clause, in order for this thing to be satisfied, okay, we are looking at the satisfaction problem of CNF, by the way, because when you're in CNF, validity problem is easy. So I'm only discussing satisfiability problem, okay? So every clause has to be satisfied. If one of the clauses is unit, then you know that particular variable, what truth value that has to take, okay? If it is a positive unit, a positive literal in that unit, then it has to take 1, or it has to take false, right? So what unit resolution does is, informally, if there is a unit clause, which implies a decision on that variable, it plugs that into the rest of the clauses and simplifies them. That's all, okay? That's all it does. Now, in this case, there are no unit clauses to begin with, and therefore BCP does not result in any simplification. So all of them remain unresolved. Okay. So here I'm using black, to unresolved clauses. Okay. So this is a case where you have to make a DPLL. What is it saying? So it says you have to force a decision on a particular variable, and that's what what I'm showing on the right side here is the sequence of decisions I make, forced decisions on the variables, as a result of which, and then I will add that literal to the original clause, and I'll start a BCP. So every time I force a decision. So I'm choosing X1 at the first decision I make is X1 to be 1, okay? Which in the DPL procedure is like adding the literal X1 to this clause and then starting a BCP. So what will happen there, the BCP, if X1 is 1?
Like X0 becomes 0 and C1 clause changes to X2 plus
Correct.
X4.
So this is what happens, okay? So this C1 and C2 clauses gets simplified. They still remain unresolved because they're not unit. They're not even unit. Okay, they're not unit, or So this is what happens. So that's what happens as a result of decision at level 1. Now I'm once again forced decision. If I had lucked out, if all of them either had been reduced to true, then I know the procedure ends. Otherwise, or if everything, even one of them reduced to false, then I know there's a conflict. Okay, so otherwise, okay, then I make a decision on X8. Okay, yeah, 1. Therefore, C6 is the only clause which in which it appears. So that reduces to this one shown in blue. Then X7. What happens, Amir, as a result of X7?
So C5 and C6 become.
Not only that, okay, you see the BCP gets to do a lot of work in this case, as you will see. I've shown the result of it produces a lot of unit clause. Okay, this is an interesting case. Okay, so you're right. Okay, so as a result of X7 being 0, the dash dash dash, it shows that I've made a decision sign false to that. Therefore, this becomes X1. So you see, X6, okay, both these become unit. So if I made X7 to be 0 in the presence of these two decisions, then I'll have to make X6 and X5 to be 0 as well. That then will trigger further unit resolution steps, taking this to X4. That's what. These are all unit literals being produced as a result of BCP. Okay. Then this becomes X3. This becomes X2. And what will happen then? They jig. after this step?
Devjit is
Sir,
not
Devi
here,
is
sir.
not here.
Oh, I thought he did show up.
No, I think he had some internet issues. He was
Ah.
trying to join, but then I think
Yeah, I know. He said, okay, good. Then Harsh. I don't know. So, yeah. So basically, this will result in further things. So you plug that X3 bar and X2 into this, you will get conflict. So what this means is certainly that this doesn't necessarily mean that your original formula is unsat. Okay, if your initial BCP produced a conflict, then it is certainly unsat. But here you are making some forced choices. What this means is this set of choices that you have made explicitly is not the right choice. Okay? This is when you will have to backtrack, okay, in DPLL. Okay, so what you'll have to do is, and what it does is it backtrack. I mean, that's why I use the recursive thing. So in the recursive thing, you effectively what you do is you backtrack to the latest decision level, which in this case is 3, and then you explore, you flip the decision at that that you made at that level, and explore the other choice that you have of adding the other literally the other polarity. Okay, and so that's what happens as the next step. So backtracking after, so that's what I'm going to illustrate after things. So what you have here is you have up to X7. Okay. So I backtrack. When I backtrack, I'll have to, in this case, since I'm backtracking only to the earliest thing, so all the effect of simplification based on X7 being 0, I have undone. Okay, and I brought it back before the decision in X7 is done. So I'm here. So now I'll flip that decision, okay? The last decision was X7 being 0, so I'm going to be making it a 1. So which will then reduce these things to true clauses. Still there are some unresolved ones. Therefore, now I'll have to make a forced decision. Let's suppose that I choose X4 to be 0. So there are several clauses with X4. If X4 I make it to 0, this will become X5 plus X6. These two, C1 and C3, become true, correct? And yeah, so what you have is just C2 and C4, which still remain unresolved. And you see that there are those two clauses and are independently satisfiable because there's no overlap of any variables in them at all. So if you continue, you can actually choose anything appropriate for these variables. So this particular choice of X5, taking X5 to be 1 and X3 to be 1 gives me one assignment. Okay, so this is how DPLL works. Any questions here now? So the important thing for you to realize is it always uses unit resolution, which is really like choosing, looking at unit clauses and plugging the truth value implied by those unit clauses in the rest of the clauses and simplifying them. Okay, and then and then repeatedly doing that. So, but if you end up having a set of unresolved clauses, then you will have to force a decision and see if that works. If not, you will have to backtrack. Okay. Any questions here?
Sir, like, can't it detect automatically that C2 and C4 are independent, so it won't have to go through you search through them?
Yeah, but if all you care about is whether it is satisfiable or not, then it's okay. Then you can stop there. But if you're looking for a satisfying instance, like a model, because we are not just interested in checking if it is getting a yes or no answer. In addition to getting a yes or no answer for the satisfiability question, we also want, okay, SAT solvers are very useful because they do return a particular satisfying instance. And therefore, if you want to do that, then you will have to, obviously, a choice where you make x3 to be 0 and x2 to be 1 doesn't work, correct?
Yep.
Okay, so that's why you'll have to do a
Sir,
little
but that won't actually happen, right? When if you set x3 to 0, then you will basically get x2 not of x2 and x5 plus x6. But then since not of x2 is a unit 1, it will be resolved. So I don't think that is
yeah,
possible.
but that is right. Okay, that's one way of doing it, yes. So you're right. So, but still, that will require you to explore a few more decisions, isn't it? Okay, unless, yeah, but how do you get that decision? Okay, getting a yes or no answer, all it requires is, okay, you can do some optimizations. Okay, it can be clever. These are, they're mutually exclusive in terms of the variables, and then therefore I can say yes or no. Okay. But if I really want to produce, then I'll have to do a little bit of further propagation, correct? Because there are two possible satisfying instances, x3 being 0 and x3 being 0 and x2 being x3 being 0 and x2 being 1 is possibility, or x3 being 0 or x2 being 1, x3 being 0 and x2 being 0 is also a possibility. Okay, so you'll have to do some extra work if you want to get the actual satisfying instance. That's the point I'm making. Yeah. Because that will require you to do further exploration. So that's okay. Any more questions? Okay. So, but there are lots of drawback with this DPLL. Okay, and I'm going to list one by one, and then kind of give you an idea of the improvements. Okay, and these improvements are what make modern day solvers. I mean, there are 4 big improvements that are, I think 2 of which are a breakthrough improvements that gave several orders of magnitude improvement in the performance, and I want to draw your attention to that. Yeah? See, impact of the decisions on variables, which variables you pick, greatly influence your choice, because the number of times you have to backtrack, and then there is some problem of hitting the same conflict repeatedly as a result of bad decisions that you make. So here is a set of decisions where I lucked out. I'm going to, for the same problem, I'm going to, after the first conflict, after I backtrack after the first conflict, okay, this is a state I'm in. The clauses are in this state after I backtracked after the first conflict. Then, instead of making the decision x4, which is what I made there, suppose I choose x5. Okay, look what will happen. Okay, so if I chose x5 to be 0, these two will become, now I flip the decision, therefore x7 will become 1. After I flip the decision, then suppose I make x5 to be 0. So then this will become x4 plus x6. Suppose I make x6 to be 0. And this becomes x4. And you see, this is exactly a similar situation which caused the conflict that you encountered previously. Because x4 being 1 is not a good thing, because when you plug in x4, once again, you're hitting the same kind of conflict that caused, as the earlier one. Okay. As a matter of fact, you and then you can backtrack, and then if you make a choice once again x4, you get a conflict again C2. Now this is just bad luck. 2 points that I'm trying to make here. One is the order in which you make the decisions on which variables and what polarity, what truth value that you assign to them greatly influences your, the number of levels of decision that you will have to make before you get a satisfiable answer. And then there is also another thing, okay? So that is one thing that is kind of unavoidable, okay? And that is, but you can do some heuristics, etc. But here what's happening is you're getting also the same conflict. So the other idea is, here we just did not analyze this conflict. Why is this happening? First of all, the reason for this conflict is that x1 and x4 cannot be both 0, cannot be both 1 simultaneously, okay? Or rather, if one is 0, the other one has to be, one is 1, the other one has to be a 0. Yeah. So since I have made a decision, that's the reason is that this thing, not of x1 or not of x4, follows as a logical conclusion of your original set of formulas. As a matter of fact, C1 and C2 and C3 implies this condition. Therefore, if you made a decision at a certain level on x1, in this case to be 1, then since this is a logical consequence of your original set of formulas, a decision either explicit or implied of x4 being 1, well, doesn't work, okay? And therefore, if you learned this fact that indeed not of x1 or not of x4 is a consequence, then if you had this fact, then you could be maybe avoiding this thing, and that's what is the most important, another important thing, okay? So which instead of just doing thing, you just backtrack and then try arbitrarily. You try to analyze the source of the conflict. This is what I mean here. Here, the source of the conflict is that once you make a choice for x1, there is a choice for x4 which is determined. Okay, so if you somehow derived this by analyzing the conflict, then you could maybe avoid these kind of repeated running into the same kind of conflicts due to bad decisions that you make on your variables. And that is what is one very significant improvement that present-day SAT solvers use over DPLL. This conflict-driven causal learning was not known until I think it was early 80s. Until 80s, the SAT solvers used to be only using DPLL, and they were not able to scale it up beyond maybe, hundreds of variables. The DP strategy only, a few tens, DPLL, maybe a few tens of variables. Now here, you were able to scale it, a couple of orders of magnitude. So what does this do? So after every conflict, you try to analyze that, the source of the root cause of the conflict, and then you derive something called a conflict clause, which is a true fact, a true consequence, a true fact about your original set of original formula, and then add that as a new learned clause, okay, to your original. So let's look at that. Okay. So yeah.
Sir, can you do this DPLL algorithm parallelly?
No. Okay. So that's an implementation issue. I don't want to get into that. Okay. So a lot of people have explored doing parallelizing it. Somehow, it has not been very successful, by the way. Okay. Maybe some parallelization that you could use. Okay. But there isn't a whole bunch of, there is not scope for a lot of parallelism. Yes, there is scope for parallelism. Okay. If you can, because see, all the clauses have to be satisfied. Okay. Any satisfying instance has to satisfy all the clauses. Okay.
Okay.
And the source of the thing, if you can somehow identify some subsets that are there ahead of time, then maybe you could do it, but you don't know, okay, which ones you do. So there can be all kinds of dependency among the clauses, and therefore it is not very clear as to what you do simultaneously that can add value. Okay, but that's a separate subject. Okay, yes, there's scope for parallelism after doing this, but the kinds of things that I'm pointing out here, the improvements are some very based on sound logical principles that whether you use parallelism or not will give you orders of magnitude improvement. Okay.
Okay.
So one of the reasons for this thing is due to bad decisions, you'll be hitting the same kind of conflicts. Okay, which means that you'll have to do a lot of backtracking. Okay, so you certainly want to avoid it. That was apparently one of the big reasons why things were not scaling up. Okay, and that's what I'm going to show you now. So what you do is after this, now, I mean, so the idea is to somehow analyze this conflict the first time you hit it as a result of making a bad decision, x7 to be 0. Because a decision for x7 to be 0 along with x8 forces x4 to be 1. And that's what was causing, because an x4 to be 1 contradicts with your decision on x1. Therefore, if you added, somehow you learned this clause. How you actually learn that clause and how you automate the process is a separate subject. I will get to that, and let's assume for now that somehow we will get the root clause that can prevent it's a source of the conflict. Now, if I added it, that is the idea of clausal learning. Not only you learn that conflict clause that is the root cause, and therefore add the negation of that, which is what will eliminate this. And then before you make the next choice, flip the decision, you can use that. Okay, this is the conflict clause. So if you did that, what happens is, as soon as you backtrack, you say to the thing, since your decision x1 is there, this will immediately flip it forces a decision on x4, the right decision on x4. Okay? because x1 was, why is that? Because x1 was 1. So this is 0. So in this learned clause says, this is something that you will have to preserve in your forced choices. Therefore, it forces x4 to be, I mean, x1 was 1, therefore x4 has to be 0. So immediately forces x4 to be 0. Therefore, later on, when you make these things in these parts of the search proof, it will eliminate, which will inhibit you from making the same stupid decision. Okay, so that's what will happen, and you will see that after that you will get these. It results in various these things. This is not what I'm doing. I mean, and you will see that you will you can. I mean, yeah. So that is the thing. So it will no longer. I mean, you may make certain other bad decisions that may cause other conflicts. Okay. That possibility is still there. It doesn't mean that adding this conflict clause removes all possible wrong decisions, but at least this decision, it will cause one cause of the conflict. It'll eliminate, and then you can get maybe faster thing. Okay, so the main idea.
I have a doubt.
Yeah.
So when you resolve a conflict, you can. So do you start from the top of the thing again, or do you remember what x1
That's
was?
a very good point. Okay, I was deferring that thing. So you have a choice. Okay, you're getting ahead of the thing. So yeah, you're exactly right. So I'm right now. Okay, so you could do. So I mean, there are two things. Okay, yes, you have a choice. Okay, now let me. Yeah. So yes. Why? Okay, let me ask you answer by a question. Who's this who asked this question?
Ameya.
Yeah. So why do you think it would be okay why do you think it would be useful, okay, to go back from the beginning?
So you can choose completely different ones again, right? I mean, so you have avoided one conflict, but yeah, I'm not sure. Like,
no, I think yeah. So you see, okay, yeah. So let me get to that. So that is a possibility, okay. But what I want you to do is you want you to understand why in DPLL, in the basic DPLL, they chose to backtrack to the latest level. Why? Because there's a reason for that, okay. Because you want to, in order to ensure termination of this backtracking, you have to make sure that all possible choices that you have at a particular level are exhausted before you go to the next level higher, okay? Otherwise, what you may end up, okay, because every time that you backtrack, you have to undo all the decisions that you did, okay, at that level. So, if you keep, without being careful, skip decision levels, you'll have to make sure that you don't keep hitting the same conflict, okay, back when you come down, so there can be a problem with termination. So I think DPLL, the people, they chose to do this because it is easy to guarantee termination, okay. Now, there is a case to be made because you've learned a new fact about your system. Therefore, by undoing maybe some of the earlier decisions, if not all the decisions, you may avoid some earlier things. Okay, you're right. For example, this thing might have So I mean, maybe the same cause is also the same clause is also is a cause for something else. Okay. So you may influence the decision. So there is a case to be made. Okay, that's a very good question. Okay, but there's also a good reason why you can. But what I'm pointing is, even without doing that, there is some use for you to only not do the backtrack only to the latest level, because then even these kinds of conflicts can be eliminated. Okay, and then in this case, there are solutions still at this lower level. So why unnecessarily undo? Is an argument for exploring it further here. So there is a case to be made for both those things. Okay, but I'll get to that. Okay, so this what does analyze conflict? Some of the questions: how do you automate? How do you generate these conflict clauses? Okay, generation of conflict clauses by analyzing the conflict. That's a very important thing. Now, can there be multiple conflict clauses? Okay, that are multiple clauses, choices, that can prevent the same kind of conflict. And if there are, then how do you pick one or more among them? All these things are important things, okay, to consider. Okay, so I'm going to go another 10 minutes today. Okay, so I hope you will cooperate, with me, because I want to get to a logical thing. Okay, so this is one improvement. Okay, so these are things that we will revisit later. Okay, but I want you to do this, because remember that I had said, okay, SAT solvers do a lot of hidden things. Okay, one of the biggest hidden thing that it does is generating these conflict clauses. Okay, and you want to implement SAT that we talked about. You want to these are once generated, you can keep them. Okay, because they are logical consequences of your original set of clauses. So then this is the second point that Ameya already pointed out. So the other improvement was non-chronological backtracking. Okay, and so backtracking to the latest level, why not backtrack to earlier levels? Therefore, since you have learned a new, the reason to do it is, the advantage, as I already mentioned, for backtracking to the latest level is guaranteed termination. But if you can somehow guarantee termination even otherwise, why not backtrack to an earlier level? What is the advantage of backtracking? The new learned clauses may make for better earlier decisions, because I have not talked about the heuristics that SAT solvers use for making a choice of which variable to make the decision on. Okay, but all those things, they look at variables, the number of literals that occur in these variables, the size of the clauses, etc., to make the decision. Okay, so if you're learning new clauses which are sound logical consequence of the thing, so wouldn't it make sense to use the newly learned clauses in your decision, the variable decision-making process as well? That is what would be one significant advantage of backtracking to earlier levels, so that then your choice of decisions, I think, which is exactly what Amir pointed out. Yeah, so that is one thing. And the other reason is, once you learn a conflict, it can have a compounding effect on learning itself. Okay, once you learn this clause, then that may result in, especially if there is another, you immediately hit another conflict, even with this clause, then you may learn something more, which is, which can use this clause as well, this learned clause as well. Okay, so that's what I mean when I say it has a compounding effect on learning, because now you're learning on a set of clauses which also include some newly learned true facts about your original thing. And these are the two reasons why it turns out that it makes a better sense. This was another significant idea that caused a significant breakthrough. Okay, although this is not always, may not always lead to better and quicker solution, but on the whole, this is also causes great improvement. So the thing that is used is you backtrack to the earliest decision level other than the current decision level among all the literals appearing in the conflict clause. So, for example, look at the conflict clause here. Okay, here, X4 was, something that was generated. That decision on X4 was generated as and implied as a result of BCP. So in this, other than this decision level, which was X4 was generated as a result of making the decision X7, it was generated at level 3 as a result of a BCP at level 3, that one that caused the conflict. So what it says is that you backtrack to X1 because the X8 decision that you made at level 2 is not dependent at all in producing this conflict clause. In some sense, X2 is not dependent. That is kind of the thing. I mean, you need to understand why this. You need to understand the way that new conflict clauses are generated to understand what this exactly means. Okay, but nonetheless, this is yes, non-chronological backtracking is is another major significant improvement in modern day SAT solvers.
Sir,
yeah.
Is it possible that sometimes having too many conflict clauses can slow down the algorithm?
Exactly correct. Okay. So as you make progress, like I said, I mean, there can be lots of conflicts each time you generate a conflict, and then they can add, and sometimes that itself can become. I mean, the number of learned clauses can overwhelm you. Okay, so that's a possibility. Yes, that means that usually that happens when your satisfying instance is the only satisfying instance, or the lot of the satisfying instances are somewhere hidden very deep in your search tree. Okay, so yes, you're right. Okay. So usually SAT solvers have a knob, okay, which says, oh, flush all my decisions. I mean, all the conflict clauses every now and then. Okay, you could do that. Okay. So you're right. So since this is how many, because there are so many things that you can actually, there are only finitely many variables and only finitely many clauses, but still there are a huge number of them. It can. So a short answer is yes, it can be done. So there is for different problems, there can be a sweet spot. What the sweet spot is not clear. So maybe after a certain size of data itself is slowing down, then you can decide to flush it. Okay, flush it up to a certain level or all the way to 0, and then use different decision heuristics and so on. So you can also do a restart. Yes. So yes, that is also a possibility. But there was one important thing that I said. Okay, so there was this thing. So if you skip levels, there is a trickiness in guaranteeing termination. Okay, but I think the reason that this can still terminate is because every time you add a conflict clause, even though you skip levels and backtrack to an earlier level, not the latest one, that is not the latest one, you have eliminated one conflict. Okay, so even if you get back to the same level with the same set of assignments, okay, back in this case number 3, you would have eliminated one. You would have one fewer conflict to consider. Okay, therefore you're making some progress. Okay, and with a finite number of number of variables, there can only be finitely many ways. Finitely many assignments. Therefore, only finitely many wrong assignments that lead to conflicts, and therefore there can only be finitely many conflict clauses. Finitely many conflicts, and therefore each time, as long as you're eliminating one conflict, it still terminates. That is the kind of argument that you will have to use. Okay, as long as you don't keep adding the same conflict clause, you are okay. Okay, with this method. So 5 more minutes. Yeah. So in addition to these two things, CDCL, conflict-driven clausal learning. This is conflict-driven because the clauses that you learn are, done incrementally by looking at the conflicts, and they are aimed at preventing that conflict. They're non-chronological backtracking. The other thing is some advanced variable decision heuristics. And the one, people consider lots of them the one. Okay, this is a very significant patented one, which works with CDCL, considering the new clauses that are learned as well. Okay, so this is another reason, and very effective software engineering in doing BCP. Okay, in doing BCP, because BCP, as I mentioned, is the workhorse, and that requires you to pay special attention to how you implement BCP, and especially in keeping track of, you need to check when a particular clause becomes unit, or when it becomes unit or not. Okay, that is, although, so even quadratic ones, okay, procedures to check whether as a result of a decision things become unit or not can become even quadratic, because you're dealing nowadays present day SAT solvers are able to scale up to millions of variables and millions of clauses, okay, tens of millions of variables and millions of clauses, and therefore that simple task of checking even quadratic algorithms can be gating factor for scalability. And therefore, doing this, checking this whether something becomes unit or not is extremely important. And some people at Princeton, they came up with a very efficient method of doing it in constant time, okay, which is the patented way of doing it that almost all SAT solvers, present-day SAT solvers do. So these are the combination things. And then, of course, there is pre-processing called cite and encoding. Okay. So the basic architecture of this thing. So I have just 2 more slides, and I'll stop after that. So this is the thing. So you start with a BCP. This is like in flowchart form. So maybe in the interest of time, I will do this. Here is a pseudocode. By the way, this figure particularly, and a lot of the examples, maybe the examples also, I'm not so sure, is there in the decision procedure book. They also have a pseudocode there, which is a little bit terse. So the pseudocode shown here is something different than what is shown there. That's why I have shown it specifically. It's just a pseudocode which gives a little bit more detail than this flowchart. So you start with the BCP. That's what this method. So here, by the way, F is the input formula. A is the list of literals that you have generated, the decisions that you have made, okay, as in the form of literals, okay? So to start with, it's empty. So you do a BCP. That's the initial BCP here. That itself results in conflict, then it is false. If it reduces to true, then you can go back. And there is a check on whether you have or everything is all the variables have been assigned. Okay. So along the way, you collect the partial assignments. The partial assignment is what has been the decisions that have been made, and that is accumulated in A. So you start with level 0, that is the level, first level. So and you do this until you have no unassigned variables, or you have a partial set of assignments, but maybe everything reduces to true, in which case the unassigned variables, truth assignments to unassigned variables don't matter. Okay, in that, then you traverse this loop. Okay, so you go here and do a BCP. If there is a conflict, yeah, and this is the inner loop here, this inner loop here, and that is the loop here. So each time that you make an explicit decision, that is the decide, this box decide here is the one that uses the decision heuristic. So that decides on a variable, creates a literal, depending upon whether it is positive or negative, then it adds that to A. The BCP takes the original formulas and all the unit literals so far generated. Then if it results in a conflict, then you traverse this inner loop. First is you analyze the conflict. So that the result of analyzing the conflict produces two things. It produces a conflict clause in C and a decision level to backtrack to. Okay. And since we do non-chronological backtracking, B can be something which is less than or equal to the current decision level. So it adds the conflict clause to F. Now, if you have a conflict and there's no more level decisions to backtrack to, then you know that you have reached a conflict that cannot be resolved. Okay. Otherwise, if you are not backtrack to some level which is not, let's say, here the assumption is that it will assign, if beyond 0, it will assign some negative level to that. So then you do backtrack. What does backtracking do? It undoes, it removes from A all the decisions that have been made up to that backtracking level. But it keeps all the conflict clauses generated, because the conflict clauses are true regardless of your decisions, okay? Because conflict clauses are sound logical conclusion of your original set of clauses. So you can keep them even after backtracking, okay? So, and sets the level to B and then does this, okay? So this is what it does. And yes, I think I should stop here because I have reached, yeah, unless you have some questions. Yeah, what I suggest is I'm going to upload another file, okay? In the interest of time, okay, so I want to, since we are running behind, this is a file that I'll upload. And the first example is the same example that I showed you earlier, but I'm showing it with a paraphernalia. Okay, it's something that it actually simulates this pseudo code that I showed you, and it also constructs what is called an implication graph that is used as a basis to generate the conflict clause. So it it would be good if you follow the examples that I showed. Just familiarize yourself with the basics DPLL, specifically this sort of pseudo code by running this example. If you could do that, then I think it will help me to go through these slides faster, and it will save some time before I move to DPLLT on Wednesday. So with that request, I will stop unless you have some questions. Any questions?
No, sir, unrelated to this, I just wanted to ask about the assignment. Can we submit
Can you give your name? Is this Ameya?
Ameya, yeah.
Okay.
No, I just wanted to ask if submitting notebooks is fine for the assignment, a Python notebook.
let's see. Okay, so I wish
I can submit a Python file as well. I'm just
is there. Okay, so there are, yeah, see, there is some which require some pencil and paper work.
yeah. So I meant for
That-
the
for
Z3
that
models.
you can write it on paper, but I prefer a PDF. Okay.
I'm not very familiar with latex. If it's fine, can I just write it?
No. I'm not asking you to do later. You can write it, scan it, produce a PDF and send it.
Yeah. That's what I was.
Or you
Putting.
can even send a scan. I mean, PDF is does not have much space. That's all. So
The plan was to do PDF.
The other thing where you have where you want to do the thing, what I was thinking was, see, you can send me the code, but how are you doing it? Are you doing it as lib2 file using file interface?
No, I'm doing it in Python, sir, using the Z3py that the gun
If you do using Z3, that is fine. Okay.
Yeah.
But I mean, even using Z3, there are two ways of doing it. Okay. One is your modeling scheme, etc. Let's suppose that you have to give a solution to your 8 queens problem. Now you will have to express it as in some ij, in terms of some ij, correct?
Yeah.
Now that you're generating it using a program, correct? Yeah.
Yeah, correct.
Yeah. So if you could actually, I mean, see, that's up to Diganta to check. Okay. So I think it should be okay, but we may require you to produce an output file of the formula that you actually send to Z3 in the lib2 format.
Okay.
Okay, so that if you're modeling a thing, we could review it. Okay.
No, I thought that's what the first part of the question was. So if you model it like in pen and paper, right? So if, or like I didn't understand what the lib2 file is.
In addition to code, see, if you're using the API, then you don't need to produce it in a file format at all. Okay, you'll have to follow your code to really see how you're generating the formulas. Okay, so what I'm asking is, maybe when I discuss with Diganta, he may think that okay, it may be easier for you to spit out a file in readable form. Okay, of the formula. That you do. Okay, which is one additional requirement that we may ask you to do.
Okay.
Which is also doable, I think. I don't know if Madhukar is still there. I mean, I haven't. Yeah. So.
Yes, sir. I'm here.
Yeah. I mean, is it? You see the difference that I'm making? Okay, we can, if it's getting very late, we can discuss it next time and then we can communicate by next time, okay, which is third. But then what I'm asking is a pure code, okay, if you're using API, the construction of the formula is itself embedded inside your code, okay? In which case we'll have to review your code to understand what the formula that we'll be spitting out, okay? So if that's formula that you spit out, if it can be, if you can produce a lib2,
Sir, like, what if that formula is dynamic? Like, in the sense, it is changing when you have to spit out multiple answers, you have to change the formula constantly.
No, but look, the reason is, it is not going to be a multiple formula. I mean, you could, no. That part might be thing. Even when you produce multiple, like if you want to, that is applicable only if you want to produce multiple solutions to Sudoku and the other one, right? So, but still the core formula, whose satisfiability you're checking will remain the same, correct?
Correct.
Yeah. After that, if you want to generate, I don't think in any of the questions that I've asked you to generate all possible solutions. I don't remember, but I don't think I have done that. Okay. So I've asked you to see if it is, generate a solution. Okay. Now, if you want to generate multiple solutions, that will require some additional thing. And then I know that you will have to, your formulas will vary, but at least you can print out that
Actually, sir, you did say all possible solutions.
I did, is it? Okay.
Yeah.
So in which case, I know. I mean, I think at least the original one formula gives the model. So should be okay. No, but if Diganta is okay with just reviewing your code and then doing it, I thought there was just a simple utility which you could use to just generate the formula. If it is more work, then I will do that. So this is one request I have, but I will check with Diganta and then I will.
Okay, sir. I'll also just look into the lib thing. Yeah.
Okay.
Any other questions?
No, sir.
Yeah. Sorry that I went way over for today. Okay, so apologies for that. Going to.
Okay. Thank you, sir.
Yeah, you can.
Thank you.
Yeah, you can drop off.